Okay, let's calculate the pH given a Ka and a solution of a weak acid. Alright, so we're given that the pH of a 0.3, no, we're not given the pH, we're calculating the pH, but we're given that we have a 0.30 molar solution of acetic acid at 25 degrees Celsius, and we're given that the Ka for the acid is 1.8 times 10 to the negative fifth at 25 degrees Celsius. Remember, these Ks are temperature dependent. Alright, so what do we know? Well, we know that the Ka expression is the concentration of the products at equilibrium over the concentration of the acid. I don't know any of these concentrations at equilibrium, but what do I know? Oh, wait, I know some initial concentrations. One, we don't worry about water in an ice table because it doesn't enter into the Kc, its concentration does not change. So I know I have 0.30 for the acid. You assume that the initial condition there is no dissociation. So which way is the equilibrium going to shift? It is going to shift this way to set up the equilibrium. So I am going to lose some acetic acid concentration. I'm going to gain hydronium, and I'm going to gain the acetate ion concentration. So at equilibrium, concentration of the acid is 0.3 minus X, hydronium is X, and the acetate is X. We're going to assume, since the Ka is 10 to the negative 5, that there is very little dissociation going on, and we're going to call that 0.3. So Ka at 1.8 times 10 to the negative fifth is going to be equal to X squared over 0.3. X, doing the math, is then equal to 0.0023. That is equal to the hydronium concentration at equilibrium. Does my 5% check out? Yep, 5% is okay because 0.022 or 23 divided by 0.3 gives me roughly 0.8%. So I'm good on that assumption. So it does ask me for the pH. All I have now is the concentration of the hydronium. So I have pH is equal to negative the log of the concentration of the hydronium ion, which is negative log of 0.0023. And if I put that in the calculator, I get 2.64. Because I have 2 sig figs in all the numbers, I need 2 decimal places on the pH. And that is how to calculate a pH from Ka. We can do this one in class. It's an opener. Let's talk about polyprotic acids. These are acids that have more than one acidic proton. Okay, so there's actually 3, well, I should say either 2 or 3. We don't deal with much more than triprotic equilibrium equations to describe what's going on in these solutions. And they each have a different Ka. These Kas are represented by Ka1, Ka2, Ka3. And this gives you an example of some of the Kas. Now, if the difference between these Kas for the first dissociation constant and subsequent Ka values is 10 to the third or more, the pH generally depends only on that first dissociation. Right. What I wanted to do first, I'll just use this as a blank page. Say I have carbonic acid. In solution, meaning if there's water present to react with it, oh dear, it's going to set up an equilibrium where it reacts with the water to form the hydronium ion and the hydrogen carbonate ion. And I don't know why I did that. That hydrogen carbonate ion then is also going to set up an equilibrium with water where we get additional hydronium ions and the carbonate ion. Okay. This has a Ka associated with it, Ka1. This is Ka2. What else can you say about that hydrogen carbonate ion? Could it also act as a base? Sure. Because that equilibrium is at play as well, and it can act like a base, taking the hydrogen from the water and forming the hydroxide ion. Typically, when you're talking about pH of a polyprotic acid solution, the pH is only dependent on this first equation. Typically, those Kas are greater than 10 to the third difference between them, and any hydronium that you get dissociating from the second or third equilibrium is fairly small compared to the first one. If you are asked to come up with the concentration of that ion, then you do have to set up more than one ice table and look at the separate equilibriums that are present. And we'll do this one in class as well. Please do it. You should be able to do that. It's just a regular problem. And we'll go over it in class if need be. All right, so we've talked about weak acids. Let's move on to weak bases. Bases react with water to produce the hydroxide ion. In this equation we have, or in this reaction, we have the base ammonia acting as a base because it is, okay? It accepts that hydrogen ion and forms the ammonium ion and its conjugate acid, the ammonium ion. Water is acting as an acid, giving up that proton with its conjugate base being the hydroxide ion. Okay, when we talk about weak bases, there are two general types. There are neutral substances with a non-bonding pair of electrons serving as a proton acceptor. This, hopefully you recall, is a Lewis base. Most of these contain a nitrogen atom. A lot of the ones that we'll be working with are the amines, okay, where that NH bond in ammonia is replaced with an NC bond, but I still have that nitrogen with 3 bonds and a lone pair that is willing to accept a proton. You know what? I misspoke. Proton acceptor is a Bronsted-Lowry base. This is an electron pair donor, which would be the Lewis base. Okay, and then weak bases are also anions of weak acids. Anions of weak acids. So if I have the acid HA, its anion is A minus. That's in solution. If there is water present, what is that A minus likely to bond with? Remember, you can think of water as being a hydronium ion, and a hydroxide. So this is going to set up an equilibrium where the A minus is going to form that, and the hydroxide ion. And this is weak acids that will do this. Okay. Okay, if we look further at weak bases, we do have an equilibrium constant expression for those as well. Kb equal to Hb, OH, and the B minus. Again, this is going to be looking at that B minus reacting with I don't know what's going on with my writing thing. Forming Hb plus the hydroxide ion. Just like a Ka with an acid, we can use a Kb or Kb to find the concentration of the hydroxide and through it the pH. Because remember, hopefully you remember, pH plus pOH is equal to 14. You should be able to do this one. Please have this done for class. We'll work this one through with class as well. Okay, so if we continue to look at Ka and Kb, because of that autoionization of water, Ka and Kb, if we multiply them, are equal to Kw. Therefore, if you know one of them, you can calculate the other. Okay, calculate the base dissociation constant of Kb for the fluoride ion HF. We know that the, oops, Ka for HF is equal to 6.8 times 10 to the negative fourth. That is given in the chart, A chart. I'll have to supply you that one because IB charts are different than the AP ones. But anyway, I know that Kw over Ka is going to be equal to Kb. Kw is 1 times 10 to the negative 14th. Ka 6.8 times 10 to the negative 4. Doing the math, I get 1.5 times 10 to the negative 11. This is important to know because if you are talking about the Kb of the fluoride ion, the equation is this. I'm going to drop the AQs for a moment. Water goes to HF plus the hydroxide. This is my Kb. Ka is the fluoride ion plus water, HF, the acid plus water, reacting to form the fluoride ion plus the hydronium ion. These are not inverses of each other. Okay? These are not inverses. Okay? They are related through the Kw. You cannot just invert them. All right? Hopefully you can see that these two equations are different. The expression for Kb is different than the inverse of the Ka. Okay. So moving on, the acid dissociation constant for the ammonium ion, remember NH plus and water, is going to set up an equilibrium with ammonia and the hydronium ion. So this is a Kb. You can look up the Kb value for ammonium is 1.8 times 10 to the negative fifth. I'm sorry, that's Kb for this. That's Kb for the ammonia, sorry. So Ka for its conjugate acid is going to be Kw over its Kb, which is 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. So the Ka for the ammonium ion is 5.6 times 10 to the negative 10th.